Here are solutions to homework set number 10 for ECE 461. This homework looks at z-transforms, converting from the s-plane to the z-plane, and drawing the root locus in the z-plane. Now the first problem is, given a transfer function in the z-plane, what's it mean? What's the difference equation? Again, in the s-plane, you're looking at differential equations. In the z-plane, it's difference equations. It's pretty much the same procedure, just cross-multiply, multiply out the polynomial, so multiplying it out, cross-multiply, and note, z means next value, so z cubed is y 3 samples in the future. Z squared is y 2 samples in the future. Y of k plus 1, y of k, x of k plus 2, x of k plus 1. So here's the difference equation that corresponds to this transfer function. So anytime you see a transfer function in z, think difference equation. Problem 2 says, suppose I have a filter in the z-plane. My input is a sine wave. Find the output. Well, this is the same thing as in the s-plane. It's a phasor problem. Here s equals j4. That's the frequency of the sine wave. Z is e to the st. I need to know the sampling rate to convert from the s-plane to the z-plane. X is 2 minus j3. The real part's cosine, minus j is sine. So the output is gain times input. Here's the gain. That's the gain everywhere. All I care about is what's the gain at that frequency. Times the input at that frequency. Multiply it all out, I get a complex number. And what that means is the real part is cosine, minus j is sine. Just like the s-plane. In MATLAB I can do that. Input your g of s. Here's your sampling rate. So here's the numerator polynomial, denominator polynomial, k, and the sampling rate. S is j4, t is 0.01, z is e to the st, there's x. What is the gain of g of z at that point times the input? You get a complex number, and again, the real part means cosine, minus j means sine. Problem 3. If my input is a step input, now find y. In this case, I use the z-transforms. A step is z over z minus 1 times your transfer function. I want to do partial fraction expansion. So I'm going to take one of these z's and pull it outside. I'll use that later. Now, do partial fractions, and you get 4 terms. Multiply through by z. Now take the inverse z-transform. This is 0. Ignore it. 7.5 times 0.96 to the k, minus 9.5, 0.92 to the k, plus 2.08, 0.8 to the k. That's a 2.08. In MATLAB, you can do that to find the partial fraction expansion. Here's your y of z, where I pulled out a z. To do partial fractions, I'm going to evaluate at plus 1, and just a point, just epsilon to the right of 1. Evaluate g of z at that point times z minus 1, and I should get 0. As that gets smaller and smaller, that gets closer. I don't want it to be too small, because then I run into 2 numerical problems. At 0.96, there's your partial fraction term, 0.92, 0.8. So MATLAB also does partial fractions. To convert from the s-plane to the z-plane, there's a couple ways to do it. The approach I like is to say z is equal to e to the st. I know the sampling rate, I know s, I know z. So here's the poles in the s-plane. In the z-plane, z is e to the st. I need to know the sampling rate, and if I do, I know how they map. So here's the transfer function in the s-plane, transfer function in the z-plane. To get the numerator that matches the DC gain, here's the DC gain of g of s at s equals 0, DC gain of g of z at DC is equal to 1. Pick k so that the two match. And k is 0.04, so there's your gain. Now this is optional. I want to add zeros at the origin to match the delay. So let's pick a frequency, like 1 radian per second. Here's g of s at s equals j1, minus 49.5 degrees. That's my target. If I analyze g of z at that point, at DC, if I analyze g of z at 1 radian per second, I'm at minus 64 degrees. Let's add a 0. It's now minus 58 degrees. 2 zeros, minus 52. 3 zeros minus 47. So my target's minus 49.5. So it's somewhere between these two. I need 2.5 zeros at the origin. I can't do half a zero, so round down or round up. I rounded down, made it 2 zeros. Some people might do 3 zeros. Either way, you're slightly wrong. But then our result is here's your g of z, my discrete time equivalent. Problem 5 is repeat. If I change the sampling rate, changing the sampling rate's a big deal. That means everything changes. So take the answers from problem 4, throw them out and start over. With t is 0.01, recalculate the poles in the z-plane. Pick k to make the gain 1. Add zeros to match the phase delay. I want to have a phase of minus 49.5 degrees. It looks closest to 2 zeros. Not exactly right, but pretty close. So leaving it at 2 zeros, there's g of z, the sampling rate of 0.01. Again, totally different than what it was at 0.1. Change the sampling rate, you change g. Change g, change the root locus, change the compensator, everything changes. Changing the sampling rate is a big deal. Okay, next problem. Let's draw the root locus. Take g of s with the sampling rate of 0.1. That gives you this g of z. Draw the root locus. Now the root locus is really the roots to a polynomial. The math doesn't care. Is it s-plane, z-plane, w-plane? It's just roots. So root locus doesn't change. I've got 2 zeros, 4 poles. 2 of the poles go to the 2 zeros. The other 2 poles go to an asymptote. Just like we did before. It's a root locus. How you interpret it is different. In the z-plane, here's your breakaway point. Here's your damping line for a 20% overshoot. Here's your damping line for z equals 0 on the boundary between stable and unstable. Once I have the root locus, once I have the damping lines, I can design for these 3 points. Taking the first point, at any point on the root locus, g times k is minus 1. At this point, find g of z, pick k to make the gain 1, gain should be 1.02. As a check, if I have my discrete time system, here's t is 0.1. My analog g of s, I see I have a nice clean output. There's my stair step, my k of z, with the gain of 1.02. And what I expect, no overshoot, settling time is something. Anyway, that's if you're using VisSim. If I don't have VisSim, I can still use MATLAB. Here's your g of z, here's k. Close the feedback loop, gk over 1 plus gk. Now take the step response, and there's your step response with t is 0.1. Problem 8. Repeat, but now design for 20% overshoot. That's a different spot on the root locus. Again, on the root locus, here's your damping line. Root locus came together, split apart. This point was 0.66 plus j.38. At that point, pick k to make the gain 1. Analyze g of z at that point, and it's negative real. That's good. This term should be 0 to be on the root locus. Pick k to make the gain 1. K is 3.8. Plug in 3.8, I get 20% overshoot, just like I expect. Or in MATLAB, form gk over 1 plus gk, take the step response, and there's your 20% overshoot. The max key for stability is when you cross the j omega axis, or in the z-plane, cross the unit circle. The point that the root locus crosses the unit circle, here's your unit circle, was 0.67 plus j.73. Just like before, any point on the root locus, g times k is minus 1. Find g of z at this point, pick k to make the gain 1, k is 11.76. And if I try it, it should be oscillating. Here this is slightly stable. The reason it's slightly stable is I rounded down. I said 2 poles at z equals 0. Slightly overestimated the delay. Less delay means it's more stable than I expected. So it's not oscillating, it's slightly stable. In MATLAB, I can just say here's k, form the closed loop system, take the step response, and there's your oscillations. So that is homework set number 10 for ECE 461-661.